If the universe has a center, where is it? If light cannot escape beyond the edge of the universe, what is waiting for us out there? And why does a single element challenge the entire Big Bang model? Today's content is a bit longer than usual, but I hope this video can take you on a mentally and emotionally fulfilling journey. For beings like us, whose lives are short and whose understanding is limited, exploring the universe might seem absurd. Compared to the vast timescale of the cosmos, our entire lives flash by in the blink of an eye. Even the things we consider constant, such as time and space, may behave in ways that completely overturn our basic assumptions. So as you take in this content, please keep an open mind. Let's begin with one of the most fundamental questions. Where is the center of the universe? Or in other words, where did the Big Bang happen? To answer this, we need to understand the basic process of how the universe came into being. Around 13.7 billion years ago, the universe was born from an extremely hot and dense state, so extreme that even atoms could not exist. Instead, it was a seething soup of fundamental particles. From that moment on, the universe began to expand and cool rapidly, eventually allowing atoms and stars to form. This continued expansion, together with the principle that the speed of light remains constant, turned the universe into a kind of time machine. When we observe distant celestial objects, we are actually seeing them as they were long ago. Nearby galaxies appear mature, while those tens of billions of light years away appear younger and more chaotic in shape because their light has taken so long to reach us. But it's important to remember that these distant galaxies are actually as old as we are. They are no longer in the positions where we see them now, thanks to the ongoing expansion of the universe. This kind of universal expansion means there is no specific center to the universe. In fact, any location can be considered the center, because no matter where you are, everything else appears to be moving away from you. Every point in the universe is moving away from every other point. This is what we mean by a uniform expansion. Of course, the universe doesn't expand completely evenly. On smaller scales, gravity resists this expansion and pulls matter together into galaxies and galaxy clusters. Over time, matter forms long, filament-like structures we call the cosmic web, interwoven with enormous empty voids. As time goes on, these voids grow larger due to the continuous expansion of space. This expansion rate is described by what's called the Hubble constant. Currently, it's estimated that for every million light-years of distance, space stretches by about 50,000 miles per hour. This means that extremely distant objects are retreating from us faster than the speed of light, not because they're moving through space at that speed, but because space itself is expanding. As a result, there's a boundary around us, the observable universe. We can't receive light or any signals from beyond this boundary, because the expansion of space has pushed those regions away faster than light can travel. Their light will never reach us. This also means we can't know for sure whether the entire universe is finite or infinite. Even if it is finite, it likely doesn't have an edge in the traditional sense. Instead, it might be something like the surface of a sphere, finite but without a boundary. After all, the universe contains everything that exists. If there were an edge, what could lie beyond it? So we return to our original question: where did the Big Bang happen? Where should astronomers look to find its origin point? The answer is everywhere. The Big Bang didn't occur at a specific location in space. Instead, it happened everywhere, all at once, because the entire universe was compressed into a single state and has been expanding ever since. The Big Bang wasn't an explosion in space, it was an explosion of space itself, including the coordinate system we use to describe locations. Roughly 380,000 years after the Big Bang, the universe looked like what we now observe in the form of the cosmic microwave background, CMB. Although it appears in the microwave range, this background radiation can be seen in every direction with a microwave-sensitive space telescope. Back then, the universe's temperature was still around 4,500 degrees Fahrenheit. This would have emitted visible light, but due to the expansion of the universe, the wavelengths of those photons have stretched by a factor of around 1,000, turning them into lower-energy microwaves by the time they reach Earth today. Observing the CMB is like looking at the universe before any stars or galaxies had formed. It's the oldest image of the cosmos we can see. The slight temperature fluctuations visible in this background radiation were the seeds of today's galaxies, clusters, and cosmic voids. Fortunately, there are very few bright microwave sources in the universe, which means the CMB remains a relatively clear snapshot of the early universe. Could we see even further back in time? Right now, the answer is no. Before the CMB era, atoms hadn't even formed yet. Light couldn't travel freely through the dense soup of particles that made up the universe, which was still opaque. In this earliest state, the universe did not allow photons to escape. So ultimately, the center of the universe is both everywhere and nowhere. Whenever you observe any part of the sky using a microwave telescope, you're essentially looking back at a moment just after the Big Bang. As for the second question, how old is the universe, and is 13.8 billion years a reliable estimate? Modern science widely agrees that the universe is about 13.8 billion years old. While most people either accept this number without question or dismiss it outright, the actual reasoning behind it is quite understandable. Let's take a closer look at how scientists arrived at this number. Currently, we observe that the universe is expanding and cooling. Aside from gravitational forces pulling matter together, everything in the cosmos is drifting apart. The rate of this expansion is known as the Hubble constant. Present measurements suggest that for every 1 million light-years of distance, space itself stretches by about 50,000 miles per hour. From this expanding universe, one clear conclusion emerges. Matter is becoming more and more dispersed. The space between objects continues to grow. There's also a less intuitive consequence. The expansion of the universe stretches the wavelengths of light. This phenomenon is known as redshift. Light waves emitted shortly after the Big Bang were extremely energetic and high in frequency, but as they traveled through the expanding cosmos, their wavelengths stretched out continuously, eventually reaching us in the form of low-energy microwaves. This is what we previously referred to as the cosmic microwave background. This also explains why the James Webb Space Telescope is primarily an infrared telescope. The photons from galaxies billions of light-years away have been redshifted so severely by the expansion of space that we can no longer detect them using visible light. Instead, we need infrared telescopes to observe them. Photons that carry higher frequencies have shorter wavelengths and more energy, which means they're hotter. Lower frequency photons have longer wavelengths and less energy, thus they're cooler. That's why we say the universe was once hot and dense, but has now become much larger and colder. Calculating the age of the universe depends on several key assumptions and a range of observational techniques. First, based on the cosmological principle, we assume that the universe is homogeneous and isotropic on large scales. This means matter is roughly evenly distributed, and the laws of physics are the same everywhere. We also assume that the Big Bang was a universal event, and within the framework of general relativity, these assumptions tightly link the universe's age with its expansion history. Next, we use various observational methods to measure that history. One key method is the standard candle approach, which uses celestial objects with known intrinsic brightness, like type 1a supernovae, to estimate distances based on how dim they appear. This allows us to determine how far away and how far back in time we're looking when we observe them. Another method involves analyzing the cosmic microwave background itself. By studying the tiny temperature and density fluctuations in the CMB and correlating them with the large-scale structures we see today, like galaxy clusters, we can reconstruct how the universe has expanded and evolved from its earliest stages to the present. Finally, by combining our current measurements of the Hubble constant with this expansion history, along with estimates of the universe's composition, approximately 68% dark energy, 27% dark matter, and 5% ordinary matter, scientists can use cosmological models based on general relativity to precisely calculate the universe's age. As for dark matter and dark energy, we still know very little about their true nature, but we can observe the effects they produce. Dark energy is thought to be the driving force behind the universe's accelerated expansion. Without it, cosmic expansion should have slowed by now. Dark matter, on the other hand, is an invisible substance we can't see directly, but whose gravitational effects are clearly observable, especially in galaxies and galaxy clusters, where the gravitational pull exceeds what visible matter alone could explain. Dark matter is believed to provide the additional gravity needed to hold galaxies and cosmic structures, like the filamentary web of the universe, together. In fact, we can even map the distribution of dark matter's mass, even though we don't know what it actually is. Fortunately, when it comes to calculating the age of the universe, we don't yet need to understand the true essence of dark matter or dark energy. We just need to account for their influence. So where does all this lead us? We now understand the current rate of cosmic expansion, the Hubble constant. We know how that expansion causes light to redshift. We have a fairly accurate understanding of the universe's composition: ordinary matter, dark matter, and dark energy. We accept the basic properties of the universe: its large-scale uniformity and isotropy. We can observe how galaxies evolve over time, and we can analyze the fluctuations in the CMB. By combining all this information and working backward through the laws of physics, we're able to trace the timeline of the universe all the way back to the Big Bang. In the early stages of cosmological research, scientists used three major observational approaches: measuring the Hubble constant, analyzing the cosmic microwave background (CMB), and studying the evolution of large-scale structures. These methods focused on different aspects of the universe, yet they all converged on a remarkably consistent estimate for the universe's age, approximately 13.8 billion years, with a margin of error of about 1%. So does this mean we now have a definitive answer to the universe's age? Not quite. We can say that this is our best approximation for now. As our observational technologies improve, particularly with instruments like the upcoming Nancy Grace Roman Space Telescope and the already revolutionary James Webb Space Telescope, we will be able to peer further into the ancient past of the cosmos. If future discoveries revise our understanding of the universe's age, it won't be surprising, it will be thrilling. The truth is, although cosmology has been studied for some time, we are still very much in the early stages of exploration. A few centuries ago, who would have imagined that humanity could even attempt to calculate the age of the universe? This brings us to the third question. How can a single element challenge the Big Bang model? It all begins with a fundamental question. What did the universe look like at the beginning, and how did it all start? Based on accumulated knowledge and astronomical observations, scientists developed the Big Bang model, a theoretical framework attempting to reconstruct the earliest moments of the universe. A significant part of this model relies on interpreting the spectra of elements. But as anyone who's tried to complete a puzzle knows, sometimes there's that one piece that just doesn't fit anywhere. It feels like you must have made a mistake, but you can't figure out where. That puzzle piece, in this case, is lithium. The central mystery is this: where did the universe's lithium go? Lithium is an alkali metal with 3 protons in its nucleus. It belongs to the rare class of elements that were formed just a few minutes after the Big Bang through a process called Big Bang nucleosynthesis, BBN. Along with hydrogen and helium, lithium should have emerged in small quantities during those early moments when the universe was still extremely hot and dense. So how does this challenge the model? According to the hot Big Bang theory, the universe began expanding and cooling from an extremely hot and dense origin. Although the initial singularity is poorly understood, where known physical laws break down, the moments after the Big Bang are somewhat better described. Between 1 second and a few minutes post-Big Bang, the temperature dropped to around 1 billion degrees Kelvin, allowing nuclear forces to bind protons and neutrons together. In this window, hydrogen formed in large quantities, around 76% by mass, followed by helium, about 24%. The model also predicts that through rare nuclear reactions, a small amount of lithium, particularly the isotope lithium-7, should have been produced. Detailed calculations suggest that lithium-7 should make up about 0.00000007% of the universe's mass. This precise prediction of lithium abundance forms the crux of the lithium problem, because it does not match what we actually observe. This discrepancy is the heart of the lithium mystery. While the Big Bang nucleosynthesis model accurately predicts the observed abundances of hydrogen and helium, matching what we see in stars and ancient galaxies, it runs into trouble with lithium. There are two main issues. First, the observed abundance of lithium-7 is significantly lower, about 1/3, than what the theory predicts. Second, the isotope lithium-6, which is supposed to be extremely rare, just 2 parts in 100,000 of total lithium, appears to be much more common than expected, up to 1,000 times more abundant than the model suggests. These two inconsistencies, the underabundance of lithium-7 and the overabundance of lithium-6, combine to create a serious challenge for the Big Bang model. So what does the lithium problem imply? Do we need to discard the entire Big Bang theory? Not necessarily. When theoretical predictions and observations conflict, there are typically two possible explanations. Either our theoretical model is flawed or our observations are incorrect. Regarding the model, completely abandoning the Big Bang theory is difficult because it successfully explains so many other phenomena, like the cosmic microwave background and the observed abundances of hydrogen and helium. Still, the model isn't perfect. Our understanding of the universe's earliest moments is incomplete. Even Stephen Hawking changed his views over time. It's possible that future updates to the model will incorporate new physics or deeper insights into the early universe, allowing the lithium discrepancy to be resolved without abandoning the overall framework. On the observational side, measuring trace amounts of lithium from the early universe is incredibly difficult. Current methods rely heavily on analyzing the light spectra of ancient stars. However, processes within stars might deplete lithium-7 or produce lithium-6, which would mean the surface measurements don't necessarily reflect the original primordial abundances. In other words, the discrepancy could be the result of systematic errors or limitations in our ability to observe the earliest traces of lithium in the universe. This discrepancy may be due to observational challenges, and perhaps with more precise data in the future, the observed values will align with theoretical predictions. In short, the lithium problem either points to the need for revisions or additions to the Big Bang model, or it reflects the current limitations of our observational methods. Ultimately, any theory about the origin of the universe cannot be considered complete until all its predictions align with all available observational data. Whether it's the lithium anomaly or any other puzzling cosmic phenomenon, all these figures must eventually be explained coherently. There's still so much we need to learn about the origin of the universe. And yet, it's almost unbelievable that, using only telescopes and human intellect, we're able to deduce events that occurred billions of years ago, long before matter as we know it had even taken shape. The grand narrative of how everything began remains incomplete, waiting for us to fill in the pieces. However the universe came into being, it rests on an underlying order, an order that allows us to uncover its rules, explore its mysteries, and reconstruct the evolutionary path of its many parts. This leads us to the next profound question. What lies beyond the observable universe? In ancient times, human tribes would gather around flickering fires, wondering what unknown forces might be lurking in the darkness beyond. From that perspective, not much has changed. Today, our fire may be brighter, our reach wider. Our vision spans the globe, and with tools like the James Webb Space Telescope, even extends to the farthest edges of the observable universe. But no matter how far we look, there is always darkness beyond the light, leaving infinite room for imagination. The edge of the observable universe represents a hard boundary, regions of space that are receding from us so rapidly that not even light can reach us from beyond that line. Nothing from those outer regions, including photons, can ever arrive here. That means anything beyond the boundary is causally disconnected from us. It can never influence us, nor can we influence it. Unlike the shadows faced by our ancestors, this particular darkness is, by its very nature, permanently unreachable. Or so we thought. In 2008, a study analyzing hundreds of galaxy clusters revealed something strange. These clusters appeared to be drifting collectively in the same direction, toward the edge of the observable universe. Their motion exceeded the limits of what our current physics could explain. It was almost as if something beyond the cosmic horizon was pulling on them, or had once pulled on them in the distant past. The gravitational influence appeared to extend across billions of light years. It suggested that some massive structure could be hiding beyond the final veil of darkness. This collective, large-scale motion of galaxy clusters became known as dark flow. How much do we really know about it? What could be causing it? And what does it mean for our understanding of the cosmos? This brings us to the fifth question. Is dark flow real? And what does it mean for our view of the universe? Dark flow is a highly controversial topic, so let's begin with what we know for certain. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, WMAP, tasked with creating a precise map of the cosmic microwave background radiation, a faint afterglow of the Big Bang that permeates all of space. The goal was to help scientists better understand the universe's structure and composition. That map, completed in 2010, profoundly shaped modern cosmology. It helped answer critical questions like how flat the universe is, and how much of it is made of ordinary matter, dark matter, and dark energy. At NASA's Goddard Space Flight Center, a research team led by Alexander Kashlinsky attempted to compare WMAP's CMB map with data on the movement of known galaxy clusters, hoping to find patterns in their motions. This was an incredibly difficult task. Kashlinsky's team used a subtle phenomenon called the kinematic Sunyaev-Zeldovich effect. This effect is extremely faint, but in simple terms, here's how it works. When photons from the CMB pass through a galaxy cluster filled with high-energy electrons, they gain or lose a small amount of energy through inverse Compton scattering. This can happen either because the cluster is hot, boosting the energy of passing CMB photons, or because the entire cluster is moving rapidly and can transfer kinetic energy to the photons. The result is that CMB radiation slightly increases or decreases in energy as it passes through these clusters, depending on their direction of motion. By analyzing these tiny changes in photon energy, scientists can infer not only the presence of galaxy clusters, but also their motion relative to the CMB. The problem is that the energy change involved in detecting this motion is incredibly small. To notice it at all, researchers had to conduct a statistical analysis of a large number of galaxy clusters. They needed a highly detailed map of the cosmic microwave background, CMB, and then compared it with the positions of about 1,000 known clusters to look for patterns in their motion. To their surprise, they discovered a trend: a large-scale, coherent flow of galaxy clusters relative to the CMB reference frame. This flow spans a cosmic region at least 2.5 billion light-years across. These galaxy clusters appear to be collectively moving at speeds between 600 and 1,000 kilometers per second in the direction of the constellations Centaurus and Vela. The mystery lies in the fact that there are no known structures, like vast superclusters, in that region of the observable universe, large enough to generate the gravitational pull required to explain such motion. This suggests the presence of one or more massive gravitational sources beyond our line of sight, perhaps even beyond the observable universe itself. This idea is controversial. After all, is it really possible for something beyond the observable universe to exert gravitational influence on our side? At first glance, the answer seems to be no. As mentioned earlier, once a region of space is receding from us faster than the speed of light due to cosmic expansion, it becomes causally disconnected from us. We can no longer interact with it, not even via gravity, because gravitational effects also propagate at the speed of light. But there's a loophole. If the interaction occurred during a particular stage in the early universe, specifically before the period known as cosmic inflation, then it may still be detectable today. To explain briefly for those unfamiliar, in the 1970s, scientists were puzzled by something called the horizon problem. Why does the universe appear so flat and so uniform in temperature and matter distribution on vast scales, even between regions that should never have been in causal contact with each other? How could such distant parts of the universe be so similar? Physicist Alan Guth proposed a solution. If the universe had once been in close thermal equilibrium, like dye thoroughly mixed in water, then underwent an extremely rapid, exponential expansion in the tiniest fraction of a second after the Big Bang, this could explain everything. That explosive growth phase is what we now call inflation. While the exact timing is still debated, physicists believe inflation occurred between 10⁻⁶ and 10⁻⁴ seconds after the Big Bang. Although it lasted an unimaginably short time, During that period, the universe may have expanded by a factor of 10 quarts or more. Imagine a bacterium swelling to the size of the Milky Way in a fraction of a second. Incorporating inflation into the Big Bang model has the benefit of explaining how even widely separated regions of space had once been in contact, allowing for a smooth, uniform universe today. So how does this relate to dark flow? The key idea is that dark flow may be a residual effect from pre-inflation conditions. Imagine that before inflation, the early universe had an uneven matter distribution. Perhaps there was a region of exceptionally high density near what would later become our observable universe. That massive region could have exerted a strong gravitational pull on nearby matter, including what would become galaxy clusters. Then inflation occurred. That massive source of gravity was flung so far away that it now lies beyond our observable universe. We can no longer see it or feel its gravity directly. But the matter it once pulled, those galaxy clusters, retain their motion, as predicted by Newton's first law of inertia. Objects in motion remain in motion, so those clusters continue to drift in the same direction long after the gravitational source vanished from our view. This is the phenomenon we now call dark flow. However, the idea remains highly controversial for two main reasons. First, it challenges the principle of cosmic homogeneity. The existence of dark flow implies that there must be an exceptionally massive region of matter outside the observable universe. That directly contradicts the original motivation behind inflation theory, which was to explain the universe's large-scale uniformity. Our observable universe appears homogeneous and isotropic. On large scales, matter density is similar in all directions, and the average motion of galaxies cancels out. This foundational principle is known as the cosmological principle, and it underpins all of modern cosmology. Dark flow, if real, implies that beyond the cosmic horizon, the universe might suddenly become uneven. A massive concentration of matter may still exist, we just can't see it. This idea is deeply unsettling to many scientists because it raises profound implications. If the universe is not homogeneous beyond what we can observe, then what does that say about our place within it? Are we simply living in a cosmic bubble within a much larger, radically different universe? What if we are just cosmological lucky ones, beings who happen to live in an unusually flat and uniform region of the universe? What would that mean for our theories about the formation of the cosmos and inflation itself? If inflation was meant to explain a universe that turns out to be not so uniform after all, does that undermine its very purpose? This brings us to the second major issue. The observational evidence itself is under debate. The existence of dark flow is not conclusively established. The team led by Kashlinsky at NASA firmly believes they have detected dark flow. However, the European Space Agency's Planck satellite team, using data from the more advanced and higher-resolution Planck Observatory, an upgrade over the Wilkinson Microwave Anisotropy Probe, MAP, conducted their own analysis of the cosmic microwave background and re-examined the same issue. After analyzing data from around 1,000 galaxy clusters, the Planck team reported that they found no statistical evidence supporting the existence of dark flow. In contrast, Kashlinsky's team reanalyzed the Planck data and claimed they still saw signs of dark flow in the signal, and so the scientific debate remains unresolved. Kashlinsky's team announced in a paper that they intended to carry out a more in-depth analysis using both Planck and OMAP data in hopes of obtaining more definitive evidence. However, the results of this further study have not yet been published. For now, until more reliable data becomes available, a more cautious approach may be to assume that dark flow does not exist, or at least to remain agnostic about it. In other words, based on current understanding, we tend to believe that there is no cosmic monster lurking just beyond the visible edge of our universe, pulling tens of thousands of primordial galaxies in its wake billions of years ago. But like all things unknown, the idea certainly sparks the imagination. Science doesn't care which answers are more convenient or which theories fit more neatly within our current frameworks. Truth is truth, whether it is elegant or messy, comforting or unsettling. Maybe someday we'll uncover a definitive answer to what lies beyond the observable universe and whether dark flow is truly real. But even if we do, chances are we'll only be pushing the edge of darkness a little farther outward, just to meet another cosmic boundary, another enigma waiting to be explored. The road to knowledge is endless, and humanity's thirst for understanding, for discovering what lies beyond, will never fade.